Okay. Good afternoon, everybody. My name is Gerald Schuller from Ilmenau University of Technology, and my talk is about fast stereo audio source separation for moving sources, together with my co-author Oleg Golokolenko. And this contains a new optimization algorithm on which I will be focusing on this talk. So let's start. So first, what's our goal? Basically, our first goal here is a separation algorithm, which is able to separate two audio sources using two microphones. So you have to imagine we have a small webcam, and this webcam has two microphones, maybe in like 6 centimeter distance. And then you have two people sitting in front of it, talking at the same time, and you would like to be able to separate the two sources to understand the one or the other person. More or less like the human is able to do with his two ears. Right? When you have two people talking, you are able to focus on one or the other. The so-called cocktail party effect. Right? So basically, this is done using a stereo webcam. Or it could also be done using hearing aids. And hearing aids, you have a similar problem. You have two microphones near your ears. And the hearing aids, they should also be able to attenuate the speaker that you want to listen to, not listen to, and only keep the one that you want to listen to. Because the cocktail party effect, if you're just using hearing aids, the brain is not really able to get one or the other because often the face information is missing. Yeah, so for these applications, when you're like at a teleconference or using hearing aids, a low algorithm delay is very important. Otherwise, you easily get confused if you have too much delay. So the delay should be in the order of a few milliseconds. So it's actually quite low, and this is actually what sound cards are capable, but you basically are not allowed to add much more delay. Also, when you think about hearing aids or maybe consumer electronics, low complexity is also important, because otherwise it's simply too either expensive or you're not able to integrate it in small devices like hearing aids. Yeah, and finally you want to have a good separation and also good audio quality without annoying artifacts. So these are our goals. And this is the principle that we're using. So here on the left-hand side, you see basically the acoustic environment. Right? So these are not real boxes, but basically this is how we model what's happening on the air. So we have two sources, two speakers in this case, and you have two microphones. And you can see you have crosstalk. So there's a direct sound from speaker 1 to microphone 1, but there's also this crosstalk from microphone 1, from speaker 1 to microphone 0 in this case. And the same for the other sides. So in this way we get mixed signals in both microphones. And both microphones have two voices, but at slightly different delays. So at this microphone, source 1 comes slightly later. In this microphone, this microphone 1, source 0 comes slightly later. And microphone 0, you have source 1 comes slightly later because of the distance, the slightly different distance to the microphones. So this is what we could use. We have two microphones where the mixes have slightly different delays, and then we can basically formulate this mixing process as a matrix multiplication with delays. So basically all we have to do is to find an inverse matrix which basically inverts this mixing process, including the delays. And what you can see here is basically a simplified matrix where we have ones on the diagonal entries, which means the sound from microphone 1 to reconstructed signal 1 is unattenuated, unchanged. Right? So it goes right through. Same for the other reconstructed sounds. But then we try to mimic this crosstalk by simply a delay. So z to the minus d1 means the delay by d samples in the sampled audio domain. And this a is an attenuation factor which mimics the slightly increased attenuation due to the slightly longer distance to the other microphone. Right. So if we have a precise estimation for this delay and this attenuation, then we have a negative sign here, and that means we cancel the influence from the other source. So the influence from source 1 to reconstructed source 0 will be cancelled. Same here, and this diagonal branch. So in the matrix, these would be the off-diagonal elements. So basically we have a very simple unmixing system here, which assumes it can mainly be built using a pure delay and an attenuation. So in practice, this is often an oversimplified assumption because we also have echoes from the room, for instance. But these echoes are much weaker than the sound from one microphone to the other because they are so close to each other. Right. So often in this setup with a stereo webcam, this is actually a good assumption, but it's not perfect. Right. There are other influences, but we are able to simulate the main influences using delay and attenuation. Yeah, does it make sense so far? So this is now basically the system that we want to optimize because those coefficients, the A's and the D's, are unknown. You could guess delays because we have the distance of the microphones, but then the exact delay depends on the angle that the source comes from. Right? So we can never precisely predict it. We just can give it a range. Similar for the A's, the attenuation. Based on the distance, we could guess an attenuation, but only a range because it depends on under which angle the source appears. Yeah, so we need to find those coefficients, and in order to find those coefficients, we need to find out when these reconstructed sources are reconstructed. Right? So we need to have an optimization criterion. And this optimization criterion here could be, for instance, the mutual information. Is everybody familiar with mutual information, an information theoretic term? So basically it measures how much information two sources have in common. And it's kind of a redundancy between two streams. Right? So it measures basically how different two signals are. And what we want to reach is two reconstructed signals which are as different as possible, because otherwise there's still crosstalk if there's more commonality. And this is how we can then apply optimization. If we have an objective function which tells us how different those sources are, then we can maximize the difference or minimize the mutual information. Yeah, so this is how optimization comes into play. Yeah, and here is the formulation using matrices. So this is the mixing matrix. Basically, this is what's done in the air, right, from the speaker to the microphones. Here you can see the delays and the attenuations. And then we just need to find the inverse system, which looks like this. So you can see actually there's also this determinant here, and we actually neglect this determinant because it doesn't really matter for separation. It's just gives it a slight different sound, but it's not really so important. So for simplicity, we drop this determinant term because it makes things much easier if we don't have it. Make sense? So again, a simplification here. So using delays and amplitudes is a simplification. Dropping this term is another simplification. So basically, we just deal with this unmixing matrix and having those four coefficients to optimize. Yeah, I mentioned the objective function. So we could use mutual information, which is quite a common information theoretic term, but it's actually quite complex to compute because for each computation of this mutual information, we need two-dimensional probability density functions. So it's actually quite a lot when you have many samples. So that's why we're looking for an alternative. In this case, the Kullback-Leibler divergence. Have you heard about the Kullback-Leibler divergence? So this is basically related to mutual information, but it gets by with one-dimensional probability density functions. Right? And this is how it's defined. So here you can see this is the Kullback-Leibler divergence. If K and Q are two probability density functions, then the divergence, the KL divergence, is defined like this. You can also interpret it as you encode one distribution using the other distribution as a code, or as a basis for a code. And then this divergence gives you the information, gives you an indication how much extra information you need because of the wrong probability distribution. Right. So here, this gets larger when you have more different signals. And mutual information gets smaller when you have more different signals. KL divergence is getting larger when you have more different signals. Yeah, and then another simplification, instead of the actual histogram, we just take the time signal and treat it as a histogram. And we just normalize it to sum up as 1, and then we have a probability. And it's, I was surprised that it works, because it's actually wrong, but it's indeed working. Right? So here, this SI is the unmixed time domain signal, and N is the sample index. So you can see here the magnitude of the samples. The sample itself can be positive and negative when they come from a microphone, divided by the sum of the magnitudes of all the samples. And basically, this looks like a probability distribution, except that it's not really. Yeah, and then our resulting objective function, basically we took two KL divergences with switched roles of P1 and P0, because the KL divergence is not symmetric. And it turns out that this makes it symmetric and gives a slight advantage in optimization, but this is actually not really necessary. So KL divergence itself will be sufficient. Yeah, and here's an example of those different objective functions. Here you can see in green the mutual information. Here you can see the delay coefficient, D, in samples, leaving the other D fixed. Right? So basically we have 4 coefficients which we need to search the minimum for. Here I just have fixed attenuations, one of the delays is fixed, and I just vary one of the delays to get an example of the resulting objective function. And here's the resulting mutual information. Here in orange is the so-called eta Saito, which is again something similar to KL divergence, but often is used for speech signals. And then here in blue we have the magnitude of the KL divergence. Or APS means we take the magnitude of the signal as PDF. So we can see they all have local minima. Here you have tiny local minima. Here you have bigger local minima. And this is difficult for optimizations. When you use gradient descent, for instance, and you start, say, close to 0 with a delay, then it will be stuck in the first minimum. Because here you have derivative, the gradient is horizontally, derivative 0. So this is where we first got stuck, because this is what's used, most often is used in systems like this. You have gradient descent. Gradient descent to solve it continuously in a system. But gradient descent doesn't work here. So we tried it in the beginning, but it really gets stuck. Right? That's the problem. So often what's the approach is to basically modify the system such that the objective function becomes convex, so that you don't have local minima. So that's basically the usual approach to solve such a system. And then it becomes more complex, Often you have a transform into the frequency domain, which gives you additional delay. Right? Those systems work, but they have more complexity, more delay, and also they add artifacts. Right? So we tried a different approach. Instead of changing our system, we try to change the optimization. Try getting an optimization which can deal with local minima, which was a challenge. So we found some interesting approaches. So we have a very simple system, but a difficult optimization problem because of the local minima. Right? And that means we need an algorithm to overcome the observed local minima, because the usual gradient descent would get stuck in the local minima, resulting in bad minimization and bad separation as a consequence. Yeah, and to solve it, we came up with an optimization which is based on probabilistic optimization, which is similar to a differential evolution. So actually, this is where we started. Do you know differential evolution? So this is actually a probabilistic optimization method, which is able to deal with local minima. Right? It basically mimics evolution, or genetic evolution. And it needs no gradients, but differential evolution has a disadvantage that it's very slow. It takes a long time and it's very complex. So it's good if you have a lot of time and you want to solve a difficult problem, but it's not really suitable for real-time, low complexity applications. Right. Yeah, so that's why we came up with a variation on it, which is fast and robust and also suitable for online adaptation. Yeah, this is actually the optimization algorithm. So I call it random directions because we have random variations here. So basically we have a random vector, give it certain variance, and then start at a point, give it a random direction to test the new value of the objective function, and if this new objective function is lower, then the current point goes there. If not, we try again. So this is basically all. So basically, this is quite similar to gradient descent, but instead of gradients, which are often unreliable when we have such non-convex problems, we take some random estimate. And when you look at such very nonlinear or non-convex functions, often the gradient behaves very random anyway. And then we can actually save ourselves the hassle and the complexity of computing the gradient and just take a random vector. And in the time we compute the gradient, we already tried a few random vectors already. Right? So in the end, this might be better. It turns out it is. So we call our system IGRIS, this separation system. And it can also work over sliding windows, which means it does constant updates. For instance, if people are moving, right, which is kind of natural. Like either you have hearing aids, then you move, and then the relative position of the sources changes. Or if you're in front of a monitor with a webcam, then people in front of the monitor also will move. So the system needs to be able to update the coefficients correspondingly. The delays and attenuations will constantly change, but slowly. And this is basically what we can do here. So here you can see we have past coefficients or states, which are then used to update using our optimization. Yeah, and here's some results for the separation performance. So this uses actually random movements of the sources every 512 samples at a mean speed of 0.2 meters per second. We have a sampling frequency of 16 kilohertz for audio. Then we use 2 iterations per signal block, so it's actually quite little, right? So this random update It's actually done with just 2 random vectors for each block. But over time, it finds the right solution. And the audio duration is total 218 seconds. And here on the horizontal axis, you can see the room impulse length in seconds. So that means how reverberant a room is. And the more reverberant, the less our assumption of a pure delay holds, right? So it becomes worse. But it turns out that's the same for previous state-of-the-art approaches. So here you can see this is the least reverberant room. So we have a room impulse duration of 0.05 seconds. And the red one is our system. Trinicon here is a comparison system, and green is the unmixed version. And on the vertical axis, you can see the signal to interference ratio, which is basically the ratio between the desired signal and the unwanted signal, right? The interference. So the higher this value, the better. And you can see here, actually our system is much better than our comparison system, even though this is much more complex. Right? So it's a quite nice result. When you have more room impulse responses, the length becomes larger, then it becomes comparable. And even more comparable when you have longer impulse responses. So our system is either as good or better than the current state of the art. Right, so here you can see the signal to distortion ratio. So it's a fine line to differentiate between. So distortion actually covers artifacts, like when you use the frequency domain and you have aliasing artifacts from using the frequency domain. Right? But in this case, both iris and Trinicon don't really have aliasing artifacts, which is good. So no unnatural sounding artifacts after separation. Yeah. Makes sense so far? So basically you see our system is competitive or better than state of the art. Yeah, now I have a little real-time demonstration using a Python program. So we did everything in Python here, and I really like the programming language Python because it's a nice mix between C and MATLAB. So you can access the computer sound card, for instance, and at the same time you have high-level commands, for instance, for filter design or signal processing. So very convenient. And this actually makes it possible to do real-time implementations where you have a signal from a microphone coming in, being processed, and then played back right away. Right? So you can really simulate or actually implement such system, like for the hearing aid or the teleconferencing application. So this program takes a sound file from the stereo webcam, like I mentioned, about 6 centimeter microphones apart, and 2 simultaneous voices. Actually, Oleg's and my voice. He simultaneously talked. And first it plots the mixed voices and plays it back so that you can hear, that you cannot really understand either of us. Then it shows those different objective functions, which you already saw. Then it computes the optimum unmixing coefficients using our new algorithm. And here you can see the iterative updates. You can actually see how the objective function decreases. And you can also see how long it takes on my laptop. So on my laptop it takes less time to find the solution than the signal is long. So that means it's suitable for real-time applications. Yeah, and finally it plays the resulting unmixed voices. So let me try it and see if it works on my little speaker here. So now I let it actually run on my laptop here. Copy. Paste. Let's see. Can you see it? So this is the plot of the mixed voices. So you can see that those 2 channels, blue is microphone 1, orange is microphone 2, and this is what we get. So, hard to say.
No mixed signal, stereo. The demonstrating the noise separation is according.
So there were two voices. Did everybody hear it? So the voices were really mixed. So it's basically you cannot understand either of us. And here you can see the resulting objective functions, which we just saw. And now it optimizes. So here you can see iteration. So now it counts the iteration, and here this x0 is the objective function. Let's see here. So this is the final value of the objective function here, minus 0.07. We have the minus here because remember the KL divergence increases, becomes larger when we have more separation, but we have a minimization optimization. Right? So we want to minimize this, that's why we have the negative sign. So this is the final value for the KL divergence, 0.73, and here you can see the mutual information, 0.09, so you can actually see it reached quite a small value of the mutual information. And here you can see the obtained coefficients. So this is also kind of interesting. So the first two coefficients are the attenuations between the two microphones, from one microphone to the other. So here you can see it's 0.9 and 0.85. So quite close to 1 actually, which was to expect because they are so close, and also they are omnidirectional microphones. They don't have really attenuations to any directions. Then the second two coefficients are the delays that are found, which are optimal. And here you can see we have a delay between 5.8 samples and here 5.6 samples from one microphone to the other. And this actually roughly fits for the speed of sound between the two microphones. Right? So it's actually indeed in the correct range. So this was promising. So now you can listen to it when I close this window.
Separated channel 0. We are demonstrating the blind source separation for connected separated channel 1. The Endcast reading the Großleise and Motion frequency connecting.
So now you could understand both, right? You could still hear a little bit the other one, but it was much weaker. So this shows that this actually successfully separated the two. Did everybody hear it? Mm-hmm. No? Okay, right. So, I still find it kind of amazing that this actually works. It's basically just a random optimization algorithm that finds quite reliable the correct coefficients, even though they're behind multiple local minima. So let's continue. So now I have another example. So basically we minimize the nonlinear function, including the divergence function, in our application. We could also use our gradient-less optimization for a simple one-dimensional function with local minima to optimize, as illustration. Right? So instead of 4 coefficients, now I just have 1, which has the advantage that it's easier to plot. Right? So an example here is sum of 2 sinusoids. So I have a low-frequency sinusoid and a high-frequency sinusoid added up, and that gives many local minima. Right? And then it should find the global minima. So again, this is a nice Python example here. Started. Paste. So here you can see what's happening. It starts here at the starting point, and now I already found the global minimum. Did you see a change? Maybe I should do it again. So maybe I can make it larger. Yes, here's the starting point, and this is the global minimum. So the orange here is the global minimum I found. Maybe I can try it again. So I have to look quickly. See, it jumps down. Now it's here, and now it jumps to the final. So it gets stuck a little bit here, but then it jumped down. Now it stays here. Isn't that amazing? You can actually jump out of this global minimum. Okay. So basically this is what we got at the end of the optimization. It starts here, then goes down, stays here a little bit, and then it jumps down, and it finds the global minimum. Yeah, so it shows that our optimization of random directions is able to find the global minimum, despite the local minimum being between the starting point and the global minimum. Yeah, this can also be used for other very nonlinear functions like a deep neural network, for instance, as function approximation. And when we have a deep neural network, that's basically multidimensional, very nonlinear function. The deeper, the more nonlinear. So when we use it as function approximation, we can have an input sample, say x. In this case, it's again one-dimensional. We have one input sample and expect one output sample. So the target output, target means this is what we wish that the neural network should produce, is in this case a sinusoidal function plus noise to irritate the system. Right? So it should basically learn a sinusoid even though we have a very noisy target for our desired function. Yeah, so as in the source separation, the approximation is done sequentially, one input target pair at a time. So here we can also update, which is often desirable when you have a network. The network is trained on some training set, but then you also want to apply it to some new data and you want to also be able to learn from this new data. Right? So this is also kind of unusual for neural networks. Usually you just have the training set and after training you're done. Right? It's no longer updated. And that's because the training process is really complex and you need big machines, GPUs and fast machines for training. Right? And what I show here is that you can use my optimization for a cheap update, basically. And that means it can be done on cheap devices that you apply, for instance, to speech recognition. Right? When you have, for instance, speech recognition in your smartphone or something, you could locally update the model in this way. Yeah. So here I compare it, our approach with ADA. Do you guys know ADA? Adaptive moments. This is basically gradient descent using adaptive moments, which means it's getting inertia. Like if you have a gradient, then it doesn't stop in the first local minima, but it continues to go in the hopes that it then comes out of a local minima. Right? And this seems to work best for neural networks. Right? This seems to be the most popular one, simply because it can deal with small local minima. Yeah, and then I compare it with our method of random directions. So I have two versions. First, a deep neural network, which does the sequential update using ADA. So where it's getting one data point at a time and does an update after each new data point. And then I show you the same for our optimization algorithm. So let's take this one here. First ADA. Paste. So here you can see in green the approximation. Orange is the training target. And the point was the new data set. maybe I play it again. So here, blue is the noisy sinusoid that it's supposed to learn. And orange is what it actually outputs. So here you can see it totally fails because it didn't learn anything. So maybe I can try it again. Maybe some basis functions. So do it again. So you watch it. So the blue points are the new data points. It tries to follow those new data points, but it cannot catch up. Right? In the end, all we get is a flat line, which means it didn't learn anything. Did you see it all? Maybe my laptop is too fast. Maybe it's too fast. So, yeah, again, basis functions. Here is now our new version with our optimization of random directions. Same problem. You can see how random direction performs. As you can see, it's actually not so bad. So it indeed learned a smooth version of this noisy sinusoid here. So it learned up to here. This is where the test set ends, the training set ends, and the rest is test set, and of course it doesn't change anymore. But that was to be expected. So you can see here, it actually learned a lot more. Right? So it shows that in these very nonlinear examples, actually the optimization of random directions is even better than ADA, a very sophisticated gradient descent algorithm. So, right. So this is what we got roughly after ADA. Basically, it didn't learn much. And this is roughly what we got after our optimization of random directions. So it basically more or less learned this first period of our noisy sinusoid. Yeah, so this shows that after training on one period of the noisy sinusoid, the ADAM optimizer is not able to approximate the sinusoid using sequential training. But our optimization of random direction is able to approximate the sinusoid in this sequential training. So it's actually more powerful because it's able to deal with those local minima which are prevalent in very nonlinear systems, which happen in deep neural networks. So here in this deep neural network, it needed to estimate the coefficients, the weights of the network. Right? Is everybody familiar with neural networks? So you have weights and biases, and you need to find the right weights and biases which give you the desired output. Right? So basically, these weights and biases give you now a much larger coefficient set which we need to find here, and it was still able to do it. Unlike ADA. For ADA it was too non-convex. Yeah, that leads me to my conclusions. So our optimization algorithm indeed leads to a good estimation of the fractional delays and attenuation factors in our separation task. It overcomes local minima. It can track moving sources in real time when they are moving. Iris has comparable separation performance to state-of-the-art while having lower computational complexity and no system delay, because we just simulate those crosstalks. Iris is well suited for real-time applications on small devices and low-cost CPUs, because it's so simple. Okay. Yeah, so thanks for your attention, and now I'm taking questions.